All right, time to go teach. Hello and welcome to another episode of Tutor Tutors, where today we are going to continue our unit on the cell, our focus being on water potential. In the past few episodes, we've looked at osmosis and the way in which water diffuses across a membrane. This is another way, a more advanced way, that we can actually look and measure how water is going to move and why water is going to move. So let's look at our targets of the day. The first target is actually to define osmosis in terms of water potential. What does water potential actually mean in regards to the direction that water will move? And then we're going to explain water potential and the different components that make up water potential. And lastly, we're going to actually do a few calculations just looking at the way that water potential can be calculated and the limitations in which those calculations can be used. So that is our goals for today. Those are our different targets. Let's get this started. Here we go. So first off, what is water potential? Well, water potential, we use the Greek letter psi, where the water potential is equal on both sides. So solution 1 and solution 2, the water potentials are equal. Then we will end up with no net movement. Water will not move in either direction more than the other direction. It will move equal and opposite in that way. So this would be what we would refer to as dynamic equilibrium. If, on the other hand, solution 1 has a higher water potential than solution 2, then that means that water will naturally diffuse toward the lower water potential. So in this case, water will move from solution 1 toward solution 2 in this specific scenario. And now that we know the directions that water would move based upon water potentials, it will go from a high water potential toward the lower water potential. And that's because what water potential actually is, it's the measurement of the potential energy of the water in your solution compared to pure water. It's affected by the solute concentration, what is dissolved within your water, as well as also physical pressure. The physical pressure put upon our solution, either positive or negative pressure. This means that water potential is a combination of two different factors: the solutes that are dissolved within the water, as well as the actual pressure that can be existing upon that specific solution, whether it's in a cell or in a beaker or wherever it is. So that is the way that we are going to be thinking about water potential. And it is measured actually using units of pressure, specifically bars or kilopascals. This is our formula for water potential. Psi being the actual water potential. That is our designation for it. And it will equal psi s, the solute potential, plus psi p, the pressure potential. So now we have the water potential is equal to the pressure potential plus the solute potential. Now the solute potential is going to be something that we can calculate out. It is, first off, it measures that osmotic pressure, and it is only going to be either a 0 or a negative value. So it's less than or equal to 0. It cannot be a positive value. Pure water has a solute potential of 0. It's by adding solute that this potential is going to become more and more and more negative. The calculations for solute potential would be this. The solute potential is equal to negative ICRT. So the solute potential right here is equal to negative I. The I is an ionization constant. What that means is that is the number of particles that your solute will actually break into. For example, if this happened to be sodium chloride, NaCl, it will break down into two different particles. And so the ionization constant for that would be 2. If it were calcium chloride, which would be CaCl2, then the ionization constant would be 3, because it's the number of particles the specific solute would be broken into. C, that happens to be our molar concentration, however many moles we have per liter. R, that is the pressure constant right here. And lastly, T, that is the temperature, which would be measured in Kelvin. That is the formula that you'd have to use to calculate out the solute potential. This means that if you happen to have a pure solution of pure 100% water, it will have a higher solute potential. It would actually be 0. Then, if you started to add ions, and the more ions you added, the solute potential would become more and more and more negative. Let's look at a calculation for that. What would the solute potential be if you had a 0.5 molar concentration of sodium chloride in solution at 25 degrees Celsius? Well, to solve this out, we just have to break down the different parts. So first off, I would equal 2, because sodium chloride breaks into 2 separate particles. We already know that C, that happens to be our molar concentration, which is 0.5. So we know exactly what that would be. Next, R, that's always the same thing. It is our pressure constant. So R would always be 0.0831 liter bars over moles Kelvin every single time. And the temperature would be 298 K. And we get that by adding 273 plus the 25 degrees Celsius, because that would be the conversion to take Celsius into Kelvin. And if we were to take all these values and we were just to multiply them together, and making sure that we remember that this would end up being a negative value because it's negative ICRT, then we would end up with the solute potential as being negative 25 bars. And that would be the way that we can calculate the solute potential right here. The pressure potential, on the other hand, is the actual physical pressure that is being exerted upon our container, which could be our cell. So when we think about this, it can either be negative or positive. You can have positive pressure pushing outward or pushing inward, and you can have negative pressure where there is like more of a vacuum or a suction. An open container always is attributed to having a value of 0 pressure. So our 0 pressure potential would be in either 0 bars or 0 kilopascals. And that is a way that we can think about our pressure potential. And this is different when it comes down to the different types of cells that we typically are looking at, whether it's an animal cell or a plant cell. Because animal cells, if we were to take an animal cell and we were to put it in a pure water solution, well, what we know is that water is going to rush into our animal cell. And as water rushes into our animal cell, the animal cell will expand slightly, and very quickly it will burst. The thing is, animal cells cannot withstand any pressure on the inside of them. If they are going to have pressure exerted upon the insides of their cell, then they will end up lysing. And when they lyse, well, that is the end of that cell's existence. So animal cells cannot have a positive pressure potential. On the other hand, a plant cell, we know that a plant cell has a cell wall, and that rigid cell wall is able to withstand pressure on the inside. So when we take a plant cell and we put it in pure water, yes, water will rush in, and that's going to cause a pressure potential on the inside of our plant cell. And it is because of that pressure that this cell can end up meeting a point where there is dynamic equilibrium, even though the solute concentration might not have, and in this case, would not equalize out with the pure water. You're never going to end up with pure water on the inside of our plant cell, but water will equally move into and out of the plant cell because it has a combination. Its water potential is equal to the water potential of this outer area. At this point in time, the water potential of our solution and the water potential of our cell is equal. They are in pure equilibrium. We also know that because this beaker is pure water with just an open container, that its actual water potential is 0, because the pressure potential, because it's an open container, is 0, and pure water, because it has no concentration of any solute in it, would be 0, and it would equal to 0. But that does not mean that we can actually figure out what the different potentials are within the cell. We know that the combination of the solute potential and the pressure potential will equal 0. We know that the pressure potential will be a positive value, and it will be equal and opposite to the solute potential. They will equal 0 when we add them together. But we don't actually know what each of their values are in this specific scenario, but we do know that they will be equal and opposite. So in summary of all this, here's what we got. We know that water potential is a measurement of that potential energy for the movement of our water molecules. Our water molecules will naturally diffuse from that high concentration to that low concentration. They will naturally move in a specific direction, and they will do that passively. And what measures it is the actual water potential. That's a way that we can calculate out the way in which water will move and why it will move in the direction that it will move. It will diffuse toward the lower water potential. Water will move from a high water potential towards a low water potential. And the issue for it is it's this combination of these two different parts, the solute potential and the pressure potential. The solute potential is always going to be equal to or less than 0. It can never be a positive value. It will always be 0 or negative. And that's the way it works out. And the pressure potential could either be negative or positive depending on the circumstances. Many times with a plant cell, we're going to end up with some positive pressure on the inside, which is good because remember, those plant cells, they want to have turgor pressure. They want to have that pressure exerted upon their cell wall. And that helps them have that rigid shape that they have. Animal cells, on the other hand, cannot have a positive pressure potential because that will cause them to lyse. And that right there, that is a quick overview of water potential. Until next time, be awesome, stay awesome.